Let's look at continuity of some really well-known functions. Continuity of well-known functions. We don't always want to have to look at the definition of continuous when we're investigating a function. So we're going to say right off the bat that these types of functions are continuous. The following functions are continuous. The following functions are continuous, and this is the key. This is where all your algebra, trigonometry background comes in handy. The following functions are continuous on their domains. Okay, so if you know the domain of these functions, these types of functions, then you know where they're continuous. Okay, so let me put a colon here and we'll start listing. So perhaps the most basic type of function you encounter in algebra is polynomial functions. Polynomial functions are continuous on their domains. The domain of a polynomial function is negative infinity to infinity. So these are really nice, smooth, connected graphs with no gaps, okay? We have rational functions. Not quite as nice. Rational functions are fractions. So whenever we find the domains of these, I'm just reminding you, avoid dividing by 0, right? Because they're a fraction. So these typically have a restricted domain. You can't divide by 0. But as long as you don't do that, the function's continuous. All right. Next, how about root functions? Square roots, cube roots, etc. Roots are pretty easy to work with, but you do have to avoid even roots of negative numbers. Okay? Avoid even roots of negative numbers, and then you'll be just fine. You won't be violating any mathematical calculations. Okay? Then we have exponential functions. Exponential functions are good. They're defined everywhere. Their domain is every real number. No big deal. Logarithmic functions. Not quite as nice. What you need to do on these is ensure that the argument is positive. It can't be 0. It can't be negative. You've got your trigonometric functions, which all sort of vary. But again, some are fractions, so you avoid dividing by 0. And then lastly, let me make sure you can see what I'm writing here. I don't want to go off the screen. Yeah, we're good. Lastly, you have inverse trigonometric functions, which again, they vary widely. But these are your well-known functions. You should know the domains of these types of functions. And if you do, you can quickly state where they are continuous. Okay? So no big deal there. Let's do a couple examples just to practice a little bit, I suppose. So let's see. Determine where each is continuous. Determine where each is continuous. So number 1, let's say we have f of x equals, and I'm going to do more interesting examples as reminders. So let's say the first one we have is f of x equals the square root of x plus 2. Well, this is a root function. Its domain is going to be anything that does not make a negative number under the square root. So hopefully you understand that that's from negative 2 to infinity, and you can include negative 2. So these are the numbers that you could plug in for x and get an output. So these are the numbers that are the domain of the function. And since this is a root function, it's continuous on this entire domain. So it's continuous between negative 2 and infinity, and it's continuous from the right of negative 2, since this is an endpoint. Okay? example 2, let's say g of x equals x plus 3 over x plus 2. This is a rational function. You've got a denominator. Well, the domain of this function is anything but negative 2 for x. So the domain is negative infinity to negative 2, union negative 2 to infinity. Since it's a rational function, it's a well-known function, it's continuous on these intervals as well. Okay? Let's do one more. Let's say we have h of x equals the natural log of x plus 1. So that's a log function. And we have to make sure that x plus 1 is positive. So we're going to start at negative 1 for x and go to infinity, because all of those values will make sure that this is positive. And I don't include negative 1, because if I plug negative 1 in for x, I get an argument of 0, which is also not OK. But if I choose x values from this interval, this function is continuous at all of those x values. So there are some quick examples illustrating this concept. Now, there are a couple theorems that help us out, because what if we want to combine these common functions? What can we say about the continuity? So the first theorem says if f and g are continuous at a, some known number a, at some constant a. If f and g are continuous at a, then the following functions are continuous at a also. And so we can combine these functions using arithmetic. So if f and g are both continuous at a, then so is the sum of those two functions. So is the difference of those two functions. So is the product of those two functions, f times g. So is the quotient of those two functions. Almost true, as long as, right, we're looking at a, so as long as that denominator g does not equal 0 when we input a. So as long as g of a does not equal 0, then f over g is also continuous at that a value. And lastly, any constant c times f, or c times g, will also be continuous at that given a value. So really, any arithmetic combination of the two continuous functions will also be continuous. Very nice to know that. Makes it very simple. Okay? This eliminates us having to look at the limit definition of continuity to say that a function is continuous. All right? We can use our well-known functions with these operations to create a lot of continuous functions. Let's look at another theorem for another way to combine functions to get another continuous function. So another theorem says if, let's see, if g is continuous at a and f is continuous at g of a. Seems kind of weird so far. You'll see where we're going with this. So if g is continuous at a and f is continuous at g of a, comma, then the composition function of those two, f of g, is continuous at a. In other words, what this is saying, the conclusion is, if g is continuous at a and f is continuous at g of a, then f of g is continuous at a. So what that's saying is, if I take the limit as x approaches a of this composition function, f of g of x, that's the same thing as f of g of a. Okay? And so You should be familiar with the composition function. When you look at f of g of a is input to the g function first. So g has to be continuous at a, because that's the input to the g function. And then g of a is the input to f. That's why f has to be continuous at g of a, because that's now the input to the f function. So now we can take continuous functions. We have all that list of well-known continuous functions. We can combine them with arithmetic, but now we can also combine them with composition to create all these new classes of continuous functions. Okay? This all helps us avoid frequently having to write out all of these definitions of continuity to determine where functions are continuous. Mathematicians have already done all that legwork for us using that list of well-known functions, and then these two powerful theorems to create significant other continuous functions.